Hello, everyone. Well, we are going to talk about error. And I put together this presentation. It is kind of mathy, a little mathy. I've made it as unmathy as possible. But I want to talk about error and how error is used in model accuracy. And I think this is really important because it's important for you to understand the various ways that we validate or check the results that come out of our models. We did a little bit, tiny little bit of this in the data mining class when we did linear regression and we predicted an outcome and we compared the outcome to the actual value and then we calculated an error column. We even did some calculations of means on the error column, which when we did that was one of the 5 methods that you can use to actually calculate error. The only issue is that really actually is not a good measure of error. It's a measure of whether or not your model is above or below. But we'll talk about that in a minute. But what I'm going to go through in this presentation is in as non-mathy a way as possible. What are the 5 different ways that we can actually measure, calculate error? And then I'm going to give you an assignment. And the assignment is going to be you're going to go through a data file and you're going to calculate all of these values on that data file. So as I've indicated, we've built models, we've calculated and predicted values. We calculated errors, which is really taking the real value, the actual value, and subtracting the predicted value, and then we calculated the means of the errors. But there are better ways. So common methods to measure error. We can use mean absolute error / deviation. We can use mean error, mean percentage error, mean absolute percentage error, or root mean squared error. None of those things are going to mean anything to you unless you are already familiar with them or unless you're reading chapter 5 of the data mining book. Don't let the math intimidate you because we're going to run through each one of these. And again, I tried to keep it as unmathy as possible. Let's talk about mean absolute error. Mean absolute error is a way for us to be able to calculate the amount of error that exists in our model, in our data set. And we're doing 2 things. And if you look at the titles of each one of these, you'll kind of get what they're doing. Mean absolute error is calculating a mean, and it's using the absolute value. Okay, why do we do that? Well, let's go through this. Okay, so we're going to subtract our predicted value from our actual value. That's what gives us the initial measure. So that will give us a measure of error, and often denoted as E as the error. Some of those values are going to be positive and some of them will be negative because we're always subtracting the predicted from the actual, and sometimes the predicted is higher than the actual and sometimes it's lower. So we're going to get positive and negative amounts. When we average those and calculate the mean, we have to add all of them up. And if we just add them up, a lot of the positives are going to cancel out the negatives. So the actual number that we get is going to be a lot smaller than if we accounted for the error individually. So what we'll do is we'll convert all of those individual errors where we subtracted the predicted from the actual, and we'll take the absolute value, which allows us to drop the negative signs. Then when we add them up, we're adding up all positive values, nothing's canceling each other out, and we can calculate that mean. So it gives us the magnitude of the average absolute error. And what that really means for us is that every time a predicted value falls off of an actual value, there's going to be a value that comes in that. And so we're really going to look at that without really caring about whether it's negative or positive, what direction it goes. We're going to take a look at how big are those errors. And so that's what this one gives us, is it allows us to take away the negatives, which cancel out some of the positives, and really give us a measure of just every time we're measuring this, how far off are we? Whether we're negative or positive, we don't care. Here's an example of mean absolute error example. So we have the actual values there, and then we have the predicted values, and we have subtracted the predicted from the actual, and that gives us our error column. And in our error column, we have negative and positive values. So what we're going to do then is we're going to take it one step over, and we're going to take the absolute values, then we're going to take the mean of the absolute values, and you see that the mean absolute error down below was 1.83333. It would be very different if we were not taking the absolute values. Okay, so that's the first example of how we would calculate error. Mean error is what we did in the linear regression examples. We don't take the absolute value. What we're doing is we're taking the exact value and we're averaging that. So this is what we did in our data mining models. It's just a straight average, and we keep the negative signs. The positives do cancel out the negatives, and that's just part of this, the way that this strategy works. But this gives us an indication of whether the predictions in aggregate are over or under our average actual values. So how good was our model at predicting whether we were at predicting our actual values in aggregate? Again, because we're going to add these up. So that is probably going to come up with a number that's pretty small. And really what this is telling us is it's telling us if it's positive, it means that in aggregate, on average, our model is predicting higher than the actual values. If it's lower or if it's negative, then it's going to show us that our model is predicting lower than the aggregate or average of our actual values. So it's just really kind of a gauge. Are we higher? Are we shooting above? Or are we shooting below? Or are we pretty close? It doesn't go into the individual values and doesn't give much consideration to the individual values like when we're doing the absolute value one, but it just gives us an overall feel. Here's an example. So we have the actual values and the predicted values again, and we've calculated the error. And so we, in this case, did not use the absolute value. So I just left that column there, but we're not using it. What we're doing is we're actually averaging the error column. And you'll see that the mean error comes into 0.83333. Well, that's quite a bit lower than when we did the absolute value. So it does give us a different value, but it shows us that our predicted values in aggregate are higher. We're overshooting the actual values. Not by much, but it could be by a good amount relative to the averages of the actual and predicted values. But it's just an indicator. Are we above or are we below? Mean percentage error. Now we're going to look at taking the error as a percentage of the actual value. So we will take the error, the actual minus predicted, as a percentage of the actual value, like I just said. So to what percent of the actual value were we off? By taking the actual value dividing it by error. Actually, other way around. Take the error divided by actual value. Keep the sign on the value, so we do deal with negatives on this one. So a negative divided into a positive will result in a negative. And then we'll take the average of those percentages. So we'll give us a percentage, or it gives us actually gives us a decimal, positive or negative, about how far the predictions deviate from the actual values. And this is relative to the actual values. Many of the percentages or many of the numbers will cancel each other out. So we're probably going to get a pretty small number, and we'll do a summation of the percentage of either below or above. It's really a decimal representation of how far we are above or below. So here's an example, actual values and predicted values. We've got an error value, and so what we've done in each of these cases is we've taken the error and we've divided it by the actual value. And that gives us our percentage over there on the far right column. And so again, where there's negatives, we get negatives. And then we take those and we average those. And that gets us a pretty small number. It looks kind of, well, it's actually really small. So it's, as a percentage, if we wanted to actually convert this decimal into a percentage, it's going to show us that we're about 8%, almost 9% off relative to the predicted or the actual values. So very useful in showing us kind of how that all plays out. We can do the same thing, but we can use absolute values. So we'll do mean absolute percentage error. And it's similar to the mean percentage error, but instead we're using absolute values. So we'll do the absolute value of the error divided by the actual. And then we'll calculate that average. This one we're going to convert to a percentage. The other one we looked at decimals, so it was 0.087. This one we're going to multiply by 100, and that's how we would get to the actual percentage. So if we had done that for the MPE example, we would have had 8.7% off. Here we just do that out of matter of course. So here's our example, actuals and predicteds. We get our errors, and we have our absolute values again. So now what we're going to do is we're going to take the absolute error and we're going to divide it by the actual value, and we're going to get positive. All of them are going to be positive because we took the absolute values. We are going to take those and take an average of those. So there's the average down there, 0.181818182, and we're going to multiply that by 100, and it shows us the absolute percentage shows us that we're about 18% off, which is kind of a lot bigger than when we were only 8.7% off. But remember, we've completely looked at not only the way that we're calculating this, it's different, but we're looking at different things, right? We're looking at the absolute percentage error. We are looking at the amount of error that we have regardless of whether or not it's positive or negative. So a big negative is going to count just as much as a big positive. Where we're looking at the previous example, where we're looking at the MPE, we're looking at just what's the overall percentage that we're off. We're looking at, if we take the absolute value, I'm sorry, if we take the actual value and the predicted value is about 8.7% off in total, in aggregate. But if we're looking at this as the absolute value, then we can see that the negatives count just as much as the positives, and overall our model's about 18% off. The last one, root mean squared error, is probably the one, if I want you to remember any of them, this is the one I want you to remember because it's the one that's most commonly used pretty much everywhere. And it takes every error measurement, or we take the actual and we subtract the predicted, and then we square that value. And that, by squaring that value, it removes the negatives, because when you square a negative times a negative will result into a positive. So that's how we deal with the negatives. Then we add them all up and we take the average. Remember, these are squared values, so the overall value is going to be really huge because it's pretty big values when you get even small amounts of error. And then what we'll do is we'll take that number, that total average, and we will take the square root of it. So let's look at the example. So we have our actual and predicted, right? And then we have taken the error, and in the far right column we have squared it. So our actual, in our first example there, our predicted value was 6. We subtracted it from the actual, got an error of 3. When we square that, we get a squared error of 9. And we do the same thing for every one. You'll see that we get rid of all of the negatives, so that we add all those up and take the average. The average squared is 3.83, and then we take the square root of that. The square root of that results in our root mean squared error of 1.95. So that becomes typically the average error amongst our data set, gives us an indicator of how far we're off. So root mean squared error, it's probably the most involved, but it's the most commonly used. All right, so which one do we use? Well, that depends. Like I said, root mean squared error is used often in statistical models and provides an accurate measurement of the levels that prediction deviates from the actual. Great. If we want to see the actual derivation as a percentage relative to the sum of the actual values, we can use the absolute percentage, the mean of the absolute percentage. If we want to see our predictions in summation, how well they are above or below the actual values, we can use mean error like we did in the linear regression models in the data mining class, or the mean percentage error. That just shows us, are we running high, are we running low in aggregate compared to our actual values. And then a quick measure of how far our model is off is mean absolute error. Will just give us an idea of the total amount that we're, the average amount, I should say, that we're off, regardless of whether it's negative or positive. Just know that there's trade-offs in each one. And for more information on this, it's right at the beginning of Chapter 5 in the data mining book. And now you have an assignment. Your weekly assignment. You're going to take the data file that I have given you. It's posted into the Canvas course. You're going to calculate each of the following for this data set: mean absolute error, mean percentage error, mean absolute percentage error, and root mean squared error. And you will have to add columns to the file like I did in the example. You can do this all in Excel. And you can use the functions of ABS for absolute value, square root, and then if you want to square something, you use a little caret 2 and use those functions in Excel. Once you get those results, drop those into a Word doc, clearly label them, and then submit that for this week's assignment. Right? If you have any questions, let me know.